Alright, welcome back to another video. In this lecture, we are going to understand the concept behind gamma functions. I hope you found this interesting, right? So, first of all, what I want you to know is that I want to solve the quiz question, the gamma questions in the quiz, okay? But I want to explain the concept behind gamma functions before we tackle any problem. Okay, so what I want to start before we go to the gamma function is factorials, right? So do you know that factorials are linked with gamma functions? Then, if you don't know, today you must be aware. Okay, so now you are a student, okay? I want to assign this to you. You are a student and you are learning about gamma functions, okay? You are learning about something called gamma functions. Now, you don't know about factorials. Do you know? Okay, so if you know, let's say you know, okay? I know about factorials. So let's now talk about factorials a little bit and then we dive into the concept of gamma functions. Okay, so we know that 3 factorial is equal to, we know that 3 factorial is equal to 3 times 2 times 1. Okay, that is 3 factorial. And we know that this is basically equal to 6. I hope this is interesting, right? So 3 factorial can be expressed as 3 times 2 times 1, and that is 6. Okay, and also 5 factorial is equal to 5 times 4 times 3 times 2 times 1, right? And we know that 5 times 4 is 20, 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 120. Interesting, right? So we have 5 factorial to be 120. Okay, so now that we know this basis of factorials, now let me ask you a question. Do you know that the n factorial will be equal to, know that n factorial will be equal to n into n minus 1 times n minus 2 up to 1, right? N factorial will be equal to n into n minus 1 times n minus 2 up to what? N up to 1, right? So, but we know that this is only defined. This is only defined when n is a whole number. This is only defined when n is a whole number like 1, 2, or 3 up towards infinity. Now, what if n is not a whole number? What do we do? Right? What if n is not a whole number? So now that is where the gamma plays a role. Okay, that is where the gamma plays a role. So what if n is not a whole number and n is, let's say, half? Okay, so if n is, what if n is not a whole number? Okay, what if n is not a whole number? And let's say n is equal to half, right? Or let's say that n is equal to 2.3 decimal. Okay, what if n is not a whole number? For example, n is half or n is 2.3. Then how are you going to find the factorial? So you cannot use the factorial to determine this, right? So what do you use? Because only this is only defined for, or this only works for whole numbers, we have to then think about what? The gamma, right? So the gamma blends the factorial and it adds up non-whole numbers as well. So now you need a new function like a new function that agrees with 1. A new function that agrees with that 1 agrees with. You need a new function that agrees with factorials. You need a new function that agrees with factorials 2. And you know, when n is what? When n is an integer. When n is an integer. And 2. You also need something that also works, a function that also works when n is a decimal. When n is a decimal or fraction. When n is a decimal or fraction. So if what if n is what? A whole, n is not a whole number, right? Like n is equal to half or n is equal to 2.3, which is decimal. Now, that is when you need a function that agrees with what? Factorials. That is when n is what? An integer. And also you need a function that agrees with n when n is what? A decimal or a fraction. Okay, so step one. What do we have to do? The gamma function is a function fraction. The gamma function is a fancy factorial. The gamma function is a fancy factorial. Instead of multiplying numbers, like 3 factorial we did here as 3 times 2 times 1, which give us 6. The gamma function is a fancy factorial. Instead of multiplying numbers like 3 factorial, where we multiply 3 times 2 times 1 equals 6, it will rather do this. We define the gamma function. We define the gamma function using an integral. We define the gamma function using an integral. Now, where is it? Where is the integral? So the gamma function, the symbol is what? This, right? This is called the uppercase gamma. The uppercase gamma. So we define the gamma function using an integral, and that is uppercase gamma of n equals integral from 0 to infinity of x to the power n minus 1 of x to the power n minus 1 times e to the power negative x dx. Okay, so this is how we define the gamma function. So this is how we define the gamma function. Integral from 0 to infinity x to the power n minus 1 e to the power negative x dx. So that is the definition for gamma functions. So now, this is step 1, right? So step 2, let's check if it works like a factorial. Okay, so let's check. So step 2, let's check if it works like factorial. So what I mean is, if you have 3 factorial, you know that it's 3 times 2 times 1, and that is what? 6. Let's check in the gamma as well, that if you have gamma of 3, is it going to give you 6? So we begin with gamma of 1. So let's try 1, gamma of 1, right? So gamma of 1, okay, gamma of 1. So it means that n is equal to 1. So remember this definition. It's very important. This is the definition for what? Gamma. This is the definition for gamma. Okay, this is the definition for gamma. Okay, so now we are trying to check if the gamma works like what? The factorial. So now we are checking gamma of what? 1. This is called uppercase gamma of what? 1. Okay, so we know that n is 1. So we're going to substitute inside. All right, so from 0 to infinity, x to the power 1 minus 1 e to the power negative x dx. And this is equal to 0 to infinity x to the power 0 e to the power negative x dx. And this will give us x to the power 0 is 1. Okay, anything raised to the power 0 is what? 1. So we have 1 e to the power negative x dx. So we have 0 to infinity e to the power negative x dx. So this is what we have. And we know that this is, if you compute this integral, you are going to have 1. If you compute this integral, you are going to have 1, because gamma of what? 1 is 1. Okay, so we are going to check something right now. Gamma is very interesting. It's very, very interesting if you really understand factorials. Okay, if you understand factorials, gamma becomes very easy. So let's integrate this. You know that when you integrate this, you're going to have, so let's write it again, e to the power negative x dx, right? So when you integrate this, you have e to the power negative x divided by negative 1 from 0 to positive infinity. So negative e to the power negative x from 0 to positive infinity. So remember, if you substitute infinity inside, you're going to have e to the power negative infinity minus e to the power what? 0. and e to the power infinity is what? There is negative here, right? So negative into bracket negative, right? Negative into bracket negative. So we have, you know that e exponent negative infinity or e exponent infinity is 0, right? So we know that this, when you compute this, you're going to have positive 1, right? So this has confirmed what we are looking for. We know that gamma, uppercase gamma of what? 1 is 1. And as well, we know that 0 factorial is 1. So this has really confirmed that gamma gamma coincide with what? Factorial. Just that gamma extends to what? Decimals and what? Fractions. So this means that 0 factorial is equal to what? Uppercase gamma of what? 1. And that is equal to what? 1. And this is a true statement. Okay, this is a true statement. So please, I want you to note this very well. Take note of it. Gamma, uppercase gamma of 1 is 1. 0 factorial is 1. So there are some identities that you have to know so that the course or the topic becomes very easy for you. Now let's try another one. Let's try another one. So let's try gamma, uppercase gamma of 2, right? So we substitute that in there. We're going to have x to the power 2 minus 1, e to the power negative x, dx. So we have from 0 to positive infinity, x to the power 1, e to the power negative x, dx. And this will give us from 0 to infinity, x e to the power negative x, dx. Okay, so let's try to note some pattern here. Okay, let's try to note some pattern here. We can see that if you have this, and it's giving you 1, and it is attached to what? X again, that means you'll be having 1 as well, 1 factorial, right? We'll be having 1 factorial as well. Okay, so note, this is equal to what? 1 factorial. This result over here is equal to what? 1 factorial. So this is telling us something. So it means that when you have gamma of 2 is equal to what? 1 factorial. Gamma of 2 is equal to what? 1 factorial. Gamma of 1 is equal to what? 0 factorial. And that is equal to what? 1. Okay, so I want you to take note of this. So we can say that gamma of n is equal to what? N minus 1 factorial when n is what? A whole number. So let's draw this analysis here. Let's draw this analysis here. We can say that uppercase gamma of n is equal to n minus 1 factorial. Uppercase gamma of n is equal to n minus 1 factorial when n is a what? A whole number. So that is on a condition when n is a what? A whole number. When n is a whole number. Okay, so from the two problems that we solved, we have been able to deduct some theorem, right? So uppercase gamma of n is equal to what? N minus 1 factorial. uppercase gamma of n is equal to what? N minus 1 factorial. Okay, so what is so special about the gamma function? What is so special about the gamma? Okay, what is so special about the gamma? Now let's look at what is so special and unique about the gamma. So now we can do factorials of fractions like gamma of half, right? We know that. So we can do gamma of fractions like gamma of half, right? So uppercase gamma of half has some results, which is basically an identity of which you can't do anything about it. It's an identity and you have to keep it off head. I'm not telling you to memorize, but once you keep working a lot of problems, you keep it in there. And so uppercase gamma of half is equal to, can you tell me? So uppercase gamma of half is basically square root of pi. Uppercase gamma of half is equal to square root of pi. So this is equal to square root of pi. Okay, this is equal to square root of pi. So note it. Note it. It's very helpful. And this is a special identity. This is a special identity that we use in gamma functions. So uppercase gamma of half is equal to square root of pi. Is equal to square root of pi. What about negative half factorial? Okay, so negative half factorial is equal to uppercase gamma of half plus 1. So negative half factorial is equal to uppercase gamma of half plus 1. Negative half factorial is equal to uppercase gamma of what? Half plus 1. Okay, and that is what? Uppercase gamma of what? 3 on 2. So this is equal to uppercase gamma of what? 3 on 2. Right? And we know that we can factor half out, right? Or we can factor, we can make it uppercase gamma of half times uppercase gamma of what? 3. And we know that uppercase gamma of 3 is what? Uppercase gamma of 3 is what? Remember, we just did some examples right now. So you have to look at that. We know that uppercase gamma of 2 is 1 factorial. And we know that uppercase gamma of 1 is 1. So what is uppercase gamma of 3? So uppercase gamma of 3 is basically uppercase gamma of 3 on 2 is square root of half times square root of what? Pi. 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 So please, these are identities that you have to know them at your fingertips, and it will help you a lot in the problems of gamma. So let's continue from here. I'm not cleaning this because we are going to use it a lot. I want you to keep it. By the time we get the lesson done, it is off head. The formula for what? Gamma. So we know that uppercase gamma of 3 on 2 is half square root of what? Pi. And it's the same as negative half factorial, right? So the next thing is gamma has a rule like factorials. In everything, we have rules. even your environment, you have rules that guides you, right? At home, you have rules that guides you. In mathematics, we have rules. So as well as gamma also has what? Rules that guides it, just like factorials. So gamma has rules like factorials. Gamma has rules like factorials. So you know this, right? I know you know this. You know that 5 factorial is equal to what? Um 4 5 factorial is equal to what? 5 times what? 4 factorial. Okay? So you know that 5 factorial is equal to what? 5 times 4 factorial. Okay? 5 factorial is equal to what? 5 times 4 factorial. Right? That is something that you know. I know you know, right? We all know you know. So 5 factorial is equal to what? 5 times 4 factorial. Okay, the gamma version of this is the gamma version of this is uppercase gamma of n plus 1 equals n times uppercase gamma of what? N. Okay, the gamma version of this is uppercase gamma of n plus 1 equals n times uppercase gamma of what? N. Okay, so factorial has its way this form, gamma has its way this form. So uppercase gamma of 2, we know that is the same as 1 times uppercase gamma of what? 1, right? And that is equal to what? 1. Okay? And we know that uppercase gamma of 3 is equal to 2 times uppercase gamma of 1. Uppercase gamma of what? 2, right? And that is equal to what? 2 times uppercase gamma of 2, which is what? 2, right? So 2, right? And we also know that uppercase gamma of 4 is equal to 3 times uppercase gamma of 3. And that is equal to uppercase gamma of 3 is 2. And 2 times 3 is 6. So gamma is very interesting if only you understand factorials. So, gamma has rules. That is what I named it. So we know that 5 factorial is equal to what? 5 times 4 factorial. So the gamma version of it is uppercase gamma of what? N plus 1 equals what? N times uppercase gamma of what? N. So we know all this. So this is how you express them. Okay, so now let's move on to this session. So looking at this, we can see that the gamma also follows the same rules as what? Factorials, right? The gamma also follows the same rules as factorials. The gamma also follows the same rule as what? Factorials, because we can see that 5 factorial is what? 5 times 4 factorial. And this one too, gamma of what? N plus 1 is the same as n times gamma of what? N. Great. So it follows the same principle. So it follows the same principle. Okay? It follows the same principle. So how do you use gamma integrals? Okay, so now what we are coming to do is, how do you use gamma in integrals? Okay, how do you use gamma in integrals? So you will often see this kind of integrals in when you are talking about, when the question is feels like gamma and it is a gamma question, you see this kind of integrals. Okay, so this is the kind of integrals that you'll be seeing if the question is a family of what? Gamma. Okay, so you see something like x to the power k e to the power negative ax dx. These are the nature of integrals you'll be seeing if the question is a gamma questions. So integral from 0 to infinity x to the power k e to the power negative ax dx. Okay, so I want you to get this as well off head. I want you to get this integral to off head, because these are the nature of what integral functions you have to know. Okay, so this is a gamma function result. The result of a gamma function is what I'm coming to give to you. Uppercase gamma of k plus 1 over a to the power k plus 1. Right? This is the result of a gamma function. So if you have something of this nature, then the result should come in the form of this. Okay? So the result should come in a form of what? This. Okay, so it means that this is equal to what? This. That is the result of a gamma function. Now, so whenever you are stuck with a weird looking exponential integral, just check the nature of the integral. When you are stuck with a very weird looking integral, just check the nature of the integral and see if it has something of this nature, right? If it is of this nature, then the result should be in this form. Okay, now, does this match the gamma form? Okay, the questions that you'll be asking yourself if you see an integral question and it looks so weird, you ask yourself, the question I'm seeing, does it match the gamma form, which is this? That is the first question you ask yourself. If yes, then you can apply the formula over here. If yes, then you can apply the formula over here and then simplify. Okay, then simplify. So now let's take a question. Let's take a question to clearly understand this formula. Okay, so give me some short time and reflect on what we have done. I'll be right back with questions for us to clearly understand the concepts. Okay, I'll be right back. Okay, welcome back from the short break. So this is the first question that we are going to use. We want to evaluate this integral, right? Now, the first question we have to ask ourselves, does this match the gamma function formula or the gamma function definition? If yes, then we have to apply the formula and simplify. Okay, so my answer is yes, because this matches the formula we have right here. So how do we solve it? So we can see that our n here, okay, our n here is our n here is 5. Do you know why? Our n here is what? 5. So our n here is what? 5. I'll tell you why. So this means that we are going to have 0 to infinity x to the power 4 e to the power negative x dx. So we are going to have uppercase gamma of 5, and that will be equal to 5 minus 1, right? 5 minus 1 factorial, and that is equal to, remember, 5 minus 1 factorial, and that is equal to 4 factorial. Okay, so we know that 4 factorial is 24. We know that 4 factorial is what? 24. So we can see that this matches this, right? This matches this. So if that, you know, the reason why I said n is 5. N is 5 because if you put 5 here, you have what? 5 minus 1, and that is what? 4. E to the power negative x dx. That is right there. Now we know that for it to go into the uppercase gamma, that means what? We have to put the n there, and what? We have what? And in the factorial form, we have what? N minus 1 factorial. And that is equal to what? 4 factorial, which is giving us 24. Very easy, right? Now let's move on to question number 2. But give me some short minutes and reflect on this solution. I'll be right back with question number 2. Okay, so welcome back from the short break. I believe you have been able to reflect on the first question, the solution of it, and you've really understood it. Now let's move on to question number 2. So in the first question, the question 1 had no coefficient in the exponent, right? It has no coefficient in the exponent. But the second question is having an exponent in what? The exponent. So it means that it matches this definition. So remember, we have two definitions. We have uppercase gamma of n is equal to this, right? It's equal to this definition. And also we have integral of this equals this. So if you have a coefficient in the exponent, then it means that you have to use this, right? So that is an example that we have here. So this means that this is matching what? This. Okay, so we use this formula. Okay, so we use this formula. So we're going to say that 0 to infinity x to the power k e to the power negative ax dx is equal to uppercase gamma of k plus 1 over a to the power k plus what? 1. Okay, so this clearly tells us that our k here is what? 3, right? Our k here is 3, and our a from this question, looking at this, is what? 2. Our a here is what? 2, not negative 2, because the formula itself what? Has negative. So a here is what? 2, not negative 2. So take note. Okay, so a here is what? 2, not negative 2. So what we are going to do is that we just substitute into the formula and then we are good to go. So from here, our K is equal to what? 3 from here. We are comparing. And our A is equal to what? 2. Right? Our K is equal to what? Our A is equal to what? 2. So it means we are going to substitute into the formula. Right? We are going to substitute into the formula to get our solution. So we're going to have this from 0 to infinity, x to the power 3, e to the power negative 2x, the x equals uppercase gamma of our K is 3. So we have 3 plus 1, right? All over our A is 2. So we have 2 to the power K is 3 plus 1, right? So we have uppercase gamma of what? 4 divided by 2 to the power 3 plus 1. So we have 2 to the power 3 plus 1, which is what? 4. Okay, so this is going to give us 0 to infinity, x to the power 3, e to the power negative 2x. The x is equal to uppercase gamma of 4. So this is what makes the work difficult. If you don't know these basic identities, okay, you'll be struggling along the way. So please try to know uppercase gamma of 1, uppercase gamma of 4, no, uppercase gamma of 1, uppercase gamma of 2, uppercase gamma of 3, uppercase gamma of 4, uppercase gamma of what? 5, up to, let's say, something like 20. Okay, get to know up to uppercase gamma of what? 20, and it will be very, very helpful. It will be very, very helpful. For instance, as you have this here, as you are this point, if you know the uppercase gamma of what? 4, is going to make your work very easy. Okay, so uppercase gamma of 4 is basically 3 factorial. Okay, uppercase gamma of 4 is basically the same as 3 factorial. So we're going to have 3 factorial over 2 to the power 4 is 16, right? And what is 3 factorial? We know that 3 factorial is what? 3 times 2 times 1, right? So we're going to have 6 over 16, right? So we're going to have 16, 6 over 16, which is what? 3 over 8, right? So 6 over 16, which is what? 3 over 8. So for instance, if you have this kind of integral, okay, you don't know what to do, because this one, if you have to solve it manually using by part, you are going to go what? 3 times. You do by part 3 times, and it's a waste of time. What if you have x to the power 9? Are you going to do that kind of tedious job? No, that is where gamma is here for you. So once you know these two identities, these two definitions, once you have a problem and it's a tedious integral, just remember this and compare and check which of them is matching. If the integral is having coefficient at the exponent, that means that you use this particular one, and the result should be something of this nature. If the integral has no exponent on the exponential function, then you use this particular definition. I hope I've made myself clear. Now we have the question 2 done. Very easy, right? So now I want us to move to question number 3, but I want to give you some few minutes to reflect on this question number 2. I'll be back in few seconds. Okay. Okay, so welcome back from the short break. I believe you have been able to go through the question number 2 and you are okay with that. Now let's move on to question number 3. Okay, we are going to question number 3, of which is this uppercase gamma of 3 on 2. What is it? We want to evaluate that. Now, one thing you have to know is that if you have uppercase gamma of a fraction, right? So this is fractional gamma. This is fractional gamma. So if you have fractional gamma, then you have to use this identity. So use this identity. Use this identity. Okay? Use this identity, of which is the uppercase gamma of n plus 1 equals n times uppercase gamma of what? N. That is if the gamma is what? Fractional or fractional gamma. This is the identity that you are going to what? Use. This is the identity that you are going to what? Use. So this means that uppercase gamma of 3 on 2 will be equal to half times uppercase gamma of what? Half. Right? This means that uppercase gamma of 3 on 2 is the same as half times uppercase gamma of what? Half. And we know that uppercase gamma of half is square root of what? Pi. Square root of what? Pi. So we're going to have uppercase gamma of 3 on 2 to be what? Square root of a square root of pi on 2. Square root of pi on 2. So uppercase gamma of 3 on 2 is equal to square root of pi on 2, right? So that is for question number 3. Now let's have a short break and reflect on this particular solution. I'll be right back with question number 4. Okay. Welcome back from the short break. So with question number 4, which is we want to evaluate this integral x to the power 3 on 2 e to the power negative square root of x dx. Okay, this is what we have. We want to evaluate this. This is an integral that is involving negative square root of what? X. An integral that is involving e to the power negative square root of what? X. So with this as well, this is how we deal with it. You have to use what? Substitution. Okay, you have to use substitution to be able to what? Deal with this kind of problem. So this is question number 4. Okay, so we let u equals square root of what? X. So remember, this negative is part of what? The formula for gamma. Gamma possesses an exponential, negative exponential. So if you want to do substitution, just pick the function in front of what? The negative. Don't add the negative. Okay, so you have u equals square root of what? X. So this means that u squared is equal to what? X. That is beautiful, right? So if you differentiate both sides with respect to their variables, then you're going to have the 2u du is equal to what? The x. Okay, you want to do substitution. Now, we are going to substitute 2u du in place of what? The x. And then we substitute u in place of what? Square root of x. Right? So, we are going to have here integral from 0 to infinity 3 on 0 to infinity u to the power okay, so we know that x is what? U squared. So we are putting x u squared in place of what? X. So we have u to the power 2 times 3 on 2, right? We have u to the power 2 times what? Times 3 on 2, right? Times e to the power negative u, e to the power negative u, times the x now is 2u du. So we have times 2u du, right? So this takes off this. So we have from 0 to infinity u to the power 3 times e to the power negative u 2u du, right? So we come here, we come here. Do you know that gamma is so interesting? So we have from 0 to infinity, then u to the power 3 e to the power negative u times 2u du. So what do we do? Let's factor the constant out. So 2 out, 0 to infinity, u to the power 3 plus what? 1 times e to the power negative u du, right? So we're going to have 2 from 0 to infinity, u to the power 4, e to the power negative u du. So brilliant, so brilliant, so brilliant. So we know that this is having no coefficient of what? At the exponential function. So what are we going to use? We are going to use this particular one, right? So whenever you have a problem, an integral problem that looks tedious, right? And it has none of this form, right? You can make sure that you simplify, use substitution and simplify to have something of this nature. Once you have something of this, either of this or that, you use their identity and you're good to go. Okay, so you're going to have 2 times, you know that this right here is uppercase gamma of 5, right? Because you know that your n here is what? 5. And you know that uppercase gamma of n is what? Uppercase gamma of n is equal to what? S to the power n minus 1 e to the power x, negative x. So you know that if n is 5, then means that this part will be what? 5 minus 1, and you'll be having what? 4. Are we good with that? So it means that 2 times uppercase gamma of what? 5 will give us this particular result. See how gamma is so interesting. It makes integration so interesting. You don't stress when you have an integration problem. Okay, so you're going to have 2 times uppercase gamma of 5 is basically 4 factorial. 4 factorial. So we're going to have 4 factorial, and that is equal to 2 times 24. You know that 4 factorial is 24. So you're going to have 2 times what? 24, and that is what? 48. 48. So that means that the answer for this is 48. Ha! I love the gamma functions a lot. So it's so beautiful. Once you understand the principles, you are good to go. So the next example is example 6, right? Or example 5. Is it 6 or 5? Example 5. Okay. So example 5. Um, so example 5. So example 5. Example 5. We want to evaluate we want to evaluate from 0 to infinity x to the power 5 e to the power negative ax dx. Now, this integral is having a parameter a, right? So we want to evaluate an integral with a parameter what? A, which is integral from 0 to infinity x to the power 5 e to the power negative ax dx. So in here, we know that a is what? Greater than 0. So the question stated that a is what? Greater than 0. It's a condition, right? So if a is greater than 0, then it means that we can say that from here, we can say that our k is equal to what? 5. Comparing to this, because this is having a coefficient on the exponential function, so it means that we are using this. So if you are using this, it means that your k is what? 5. So if your k is 5, then it means that your a is equal to what? A as well. Because we are integrating, we don't know what a is. So we are saying that a should be equal to what? A. Okay, so if a is equal to a, then we can say that 0 to infinity x to the power 5 e to the power negative ax dx will be equal to uppercase gamma of 5 plus 1 over a is a, so a to the power 5 plus 1, right? So that is equal to uppercase gamma of 6 over a to the power 6. So this is telling us that we are going to have uppercase gamma of 6 divided by a to the power 6. And we know that uppercase gamma of 6 has an identity like the factorial, right? We know that uppercase gamma of 6 is the same as 5 factorial. These things, you have to take them off head. If you take them off head, hooray. Okay, so uppercase gamma of 6 is the same as 5 factorial. Whatever you have in the factorial, just reduce it by 1 when you are doing the factorial. So if it is uppercase gamma of 6, then it means that if you are looking at it in the factorial form, then you can say that n minus 1, which is going to be what? 5 factorial. Now, you know that 5 factorial is what? 120, right? So this will be what? 120 divided by a to the power 6. So interesting. I love the gamma functions a lot. So we have this function. When you evaluate it, you have what? 120 over what? 6. 120 over 6. So that is question number 6. That is question number 5. Now let's move on to question number what? 6. So with question number 6, we want to evaluate this function f of x equals 1 over uppercase gamma of alpha times x to the power alpha minus 1 e to the power negative x. So this is a probability density function of a gamma distribution, right? This is a probability density function of a gamma distribution. So that is f of x equals what? 1 over uppercase gamma of what? Alpha times x to the power alpha minus 1 e to the power minus x. And this is what? Probability distribution of a gamma distribution, right? Probability density function of a gamma distribution. Okay, And remember, x is greater than 0. S is greater than 0. Okay, so we want to verify that f of x integrates to what? 1 when alpha is what? 3. So the question is, we want to verify that f of x integrates to 1. Integrate to 1 when alpha is equal to what? 3. When alpha is equal to 3. So we want to integrate this and see if it is equal to what? 1 when alpha is what? 3. So let's check it out. So let's check it out. Okay, so we are going to substitute 3 in place of what? The alpha. Okay, we are going to substitute 3 in place of the alpha, and then we will integrate. So from 0 to infinity of the function, because we want to integrate this function f of x. So 0 to infinity of the function f of x dx, right? And this is equal to 1 over uppercase gamma of alpha now is 3. So 3 here times x to the power alpha is 3. So 3 minus 1 e to the power negative x times the x, right? And this is equal to 1 over uppercase gamma of 3 x to the power 2 e to the power negative x dx. So at this point, nothing should stop you from getting the right answer, right? So we can say that, okay, I forgot to bring the integral sign. So 0 to infinity, right? Okay. So remember that we have already done this thing. And we know that this gave us some results. Remember that this is the same as upper case gamma of what? 3. This whole integral is the same as upper case gamma of 3. Please, you have to take note of certain things. If not, this thing will not be interesting for you. So there are some few properties that you have to take note of them. So reflect on the lesson and get back very quick. So we know that this will be equal to what? 1 over uppercase gamma of what? 3 into brackets uppercase gamma of what? 3. So this whole integral symbol function, if you integrate, you get what? Uppercase gamma of 3. And we know that uppercase gamma of 3 is 2, right? So we're going to have 1 over uppercase gamma of 3 is 2. So 2 times 2, right? And that is equal to what? 1, 2 over what? 2, which is equal to what? 1. Hence, we have been able to prove that f of x equals what? 1 over uppercase gamma of what? Alpha times x to the power alpha minus 1 e to the power minus x, where x is greater than 0. We verify that the function integrates to 1 when alpha is what? 3. So that is very simple. And I know that it's very simple for everybody to do it. So this means that it satisfies the probability condition as stated over here. It satisfies the probability condition. Okay, so let me write it here. So this means that 0 to infinity of 1 over uppercase gamma of 3 from 0 to infinity x to the power 2 e to the power negative x the x is equal to 1. And this satisfies the probability condition. This satisfies the probability condition. Okay, that is so smart. So now let's move on to question number 7, right? Let's move on to question number 7, where we want to know some other kind of questions. I want to solve so many questions with you because it's so interesting. Okay, the last question will be the question from the quiz where we were asked to find that kind of integral and we were given the hint. So question number 7, is it 7 or 8? So question number 8, okay, we want to evaluate this particular integral, right? From 0 to infinity, x to the power 6 x to the power negative 4x dx. So basically, this will be a trial question for you. Okay, this will be a trial question for you. But before we do the trial work, let me solve this last example with you. But please give me some short minutes. I'll be right back for the last example, then I'll give you trial work. Okay. Okay, so welcome back from the short break. Now, we are going to evaluate this particular integrand, right? And can you see that we have some kind of roots in front of the exponential function and on top of the exponential function? So this is also a special case. So this, we have been given a hint, okay? So this is actually the quiz question. So we have been given a hint that uppercase gamma of n is equal to what? N minus 1 times uppercase gamma of what? N minus 1. So what we are going to do is that I want you to know that this is a more complex exponential integral, right? And we are going to use substitution and the gamma function to solve it. Okay, so we have to use substitution. Okay, so solution, let u equals square root of x, right? U equals square root of 3 times square root of x, right? U equals 3 times square root of what? X. So that is 3 cube root of x instead. So this is cube root of x. So if u is equal to cube root of x, then it means that u cube is equal to what? X. Okay, now this is what we have. What do we do again? Let's differentiate both sides. Okay, so when we differentiate both sides, we're going to have 3u squared du is equal to what? Dx, right? So it means that when we are doing the substitution, we'll put 3u squared du in place of what? Dx. And when we put u in place of what? Third square root of what? X. That is cube root of what? X. So we're going to have from 0 to infinity u to the power, now x is what? U to the power 3, right? So u to the power 3, all exponent what? Half, because this is square root of what? X. So all exponent what? Half, times e to the power x negative what? u, e to the power negative what? U, because we represented cube root of what? X to be what? U. So it means that this becomes what? Negative u. Then the x now is what? 3 u squared du. 3 u squared du. So let's bring the 3 out so that we have 3 from 0 to infinity u to the power 3 on 2 e to the power negative u squared du, right? So from here, we're going to have 3 from 0 to infinity u to the power 3 on 2 times u to the power 2 e to the power negative u, right? Yes, that is correct. So we're going to have 3 from 0 to infinity. Then we use indices here, right? So indices says that if you have the same base and they are multiplying, then you add the what? Exponents. So you're going to have 3 plus 3 over 2 plus what? 2. 3 over 2 plus what? 2. And that is 9 over 2. So we have u to the power 9 over 2 e to the power negative u du, right? So now, what do we have to do? We have to use the identity, right? We have to use the identity. So this is telling us something, okay? But we have been given a hint, right? We have been given a hint from the question. So we have to follow that principle. So now we have to use the property of gamma. We know that the whole of this is gamma of what? 9 on 2. The whole of that is gamma of 9 on 2. So as we can see from here. So we are using this identity, okay? We are using this identity, and we know that if we have n minus 1 equals 9 on 2, then means that n is equal to what? 9 on 2 plus what? 1. And 9 on 2 plus 1 is the same as 18, 11 over what? 2. And 11 over 2 minus 1 is the same as what? 9 over 2. So our function is going to be 3 times gamma of what? 9 on 2, right? So this is what we are going to evaluate. And then we'll have our final answer because we're given the hints from here, right? If we had not known this, that is where we'll be using this thing. But we know this identity, so there is no need for this. This is guiding us because we didn't know this and that. Now we know this and that. So every question, we are at the liberty to do it. So we're going to say that 3 into, now gamma of 9 on 2 is the same as 7 on 2 times 5 on 2 times 3 on 2, right? So it's the same as 7 on 2 times 5 on 2 times 3 on 2 times gamma of half. And we know that gamma of half is what? Square root of pi. So times gamma of what? Half. So finally, we are going to have 3 times this whole thing will give us yes, so this whole thing will give us 315 over 16, right? the whole of this will give us 315/16 times gamma of what? Half. And we know that this is a special identity, which is what? Square root of what? Pi. So we have 315/16 times square root of what? Pi. Okay? Times square root of pi. Very beautiful. You know, I've got to love gamma functions a lot. And the whole thing is I've been able to understand the principles and I've gotten the identities. Once you get the identities and you know the special identities, you know factorials, how factorials are linked with gamma, you are good to go. Nothing is difficult about that. So now, give me some few minutes. Okay, but remember, this is quiz. Question number 11, code 1. This is the quiz question. Question number 11, code 1. So the answer for question number 11, code 1 is 315/16 times square root of what? Pi. Square root of what? Pi. Okay? Times square root of pi. So that is the end of this question, solving of question and answers, right? So question and answers, that is the 10. So now give me some few minutes. I'll be right back with about 7 trial questions for you to give a trial on them, but I'll give you the final answers so that you work towards them. Okay, I'll be right back. Okay, so welcome back from the short break. I believe that whatever we did, you have been able to reflect on them and you've really understood the gamma functions. So these are your trial questions. I've given you 1, 2, 3, 4, 5, 6, 7. 7 trial questions. Now let me give you the final answers. So the first question is, evaluate integral of 0 to infinity x to the power 6 e to the power minus 4x dx. And your answer is, so, okay, let me write it here. Your answer is supposed to be 45 over 1024. So this is what you have to get when you evaluate this integral. 45 over 1024. 45 over 1024. The second trial is evaluate integral of 0 to infinity x to the power half e to the power negative 2x dx. And with that, your answer is square root of pi over 2 to the power 5 on 2. So with that, this is your answer, square root of pi over 2 to the power 5 on 2. The third trial is x to the power 7 e to the power minus x dx, right? X to the power 7 e to the power minus x dx. And with that, your answer is uppercase gamma of 8. Uppercase gamma of what? 8, which is equal to, you know that uppercase gamma of 8 is 7 factorial. And we know that 7 factorial is 5040. So this is 7 factorial, which is equal to what? 5040. That is the third trial. Now the fourth trial is evaluate integral of 0 to infinity x to the power 2.5 e to the power negative 3x dx. So with that, your answer is 3 times square root of pi over 8 times 3 to the power 3.5. So your answer is 3 times square root of pi over 8 times 3 to the power 3.5. 8 times 3 to the power 8 times 3.3 to the power 3.5. So that is for the third trial. The fifth trial is integral from 0 to infinity of e to the power negative x over square root of x dx. And with that, your answer is square root of pi, which is what? Uppercase of what? Half. So with this, your answer is square root of pi, which is what? Uppercase gamma of what? Half. So this is your answer for this particular one. Then with trial 6, your answer is, the question is integral of 0 to what? Infinity x to the power 5 e to the power minus x squared dx. Now with that, your answer is just 1. So you work your way out and you have an answer to be what? 1. The last trial question, which is question number 7. With that, the question is integral of from 0 to infinity x to the power negative x to the power 0.2 e to the power negative x dx. So with that as well, your answer is 0.918, which is what? Uppercase gamma of what? 1.2. So with this, your answer is uppercase gamma of what? 1.2. And that is what? 0.918. 0.918. So that is the answer for trial number 7. I believe this lesson has been a fruitful one and a blessing. Okay, so now let me give you some bonus tips for the end of the lesson. Some bonus tips for each problem. Each of the problem, let me give you a bonus tip. So first of all, before you do the problem, check if it matches the gamma form. Okay, check if it matches the gamma form. That is 1. 2, use the substitution when there is a square root. Okay, use substitution, right? Use substitution when there is a square root. 3, use gamma identity, which is what? Gamma of what? N plus 1 equals what? N times gamma of what? N. Use gamma identity, which is what? Gamma of n plus 1, and that is equal to what? N times gamma of what? N. That is the third tips, right? The fourth one is, for fraction cases, remember that gamma of 1 over 2 is equal to what? Square root of what? Pi. Gamma of 1 over 2 is equal to what? Square root of what? Pi. That is what? The special case. This is a special identity. And also know that gamma of 3 on 2 is gamma of 3 on 2 is the same as square root of pi over 2. Square root of pi over 2. So that is the few tips I have for you to be able to do these problems. And in all, we have been able to handle the concept of gamma functions. I believe you love it. Please do share with your friends, share with everyone, and subscribe to the channel. And I'm going to give you more updates. Until the next video, keep learning and stay inspired. Bye-bye.